Sistemas Inteligentes. Marek Druzdel es profesor en la Facultad de Ciencias de la Información de la Universidad de Pittsburg. Entre sus líneas de investigación, los sistemas de apoyo a las decisiones o la planificación estratégica de decisiones bajo incertidumbre. Miguel Ángel Artasolanda, alumno del máster de la UNED en Inteligencia Artificial Avanzada, Fundamentos, Métodos y Aplicaciones, es el autor de la entrevista.
Hello, Marek, how are you?
I'm fine, thank you. Hello.
Hello. I would like to start listing your main interests as researcher that are decision-making under uncertainty, decision-theoretic methods in intelligent systems, and user interfaces to decision support systems. Marek Druzdel obtained his PhD in 1992 and has been teaching since the early 90s. He has 130 publications, which have hit 3,016 reported citations, as can be seen in Google Scholar. So far, he has supervised 7 doctorates and has been membership of 20 PhD dissertation committees. Needless to say, he has supervised many Master of Science theses. Marek Druzdel has been part of various editorial boards and has participated in the organization of workshops, symposiums. As we can see, Marek Druzdel has a vast curriculum vitae. Among many others, one thing in your teaching experience caught my attention. You have been member of the advisory board of the program in Survival Skills and Ethics at the University of Pittsburg, by which you were awarded in 1997 with the university-wide Outstanding Mentor Award. So, to start, I would like to ask you, what do you like about teaching and why do you think it's important, this program in Survival Skills and Ethics?
Well, I think teaching is a very important part of a career of work for every academic. I was very inspired by what Richard Feynman said about this. There is a very nice book that I recommend to every scientist. Surely you're joking, Mr. Feynman. And in that book he says essentially, I could not live without teaching. I want to teach. He justifies this by 2 statements. He says, the first is, in life of every researcher, there are periods where you are inspired, when you are producing, when you are very creative and doing things, and there are also times where your inspiration is kind of at the lower end, and at those times, he says, teaching gives him the feeling of still doing something useful. So I think myself, I feel enormous satisfaction by teaching because in a way I'm creating the future. I'm bringing up my intellectual children. I'm helping them with their careers. And the second reason that Feynman points out, and I think it's absolutely true, is that teaching is a very important source of inspiration. Interacting with young people and listening to their sometimes perhaps naive questions makes you think very deeply about your own knowledge and refines your knowledge, makes it more systematic, often gives you ideas for research problems. So I truly love teaching.
Yeah, well, it sounds really interesting, but also it seems to be a kind of well, it's a very important role, about you are kind of helping these people to grow up, no? Also.
Intellectually, yes.
Intellectually, yes. So I think it's
because of course they are not my physical children, but
no.
In a university environment, I guess it's safe to say that their career is really going together with my career. So the more successful they are, my students, the more successful I am, and the more happy I am. So it's a very nice environment that I'm really happy in. And of course I have my favorite topics that I've been teaching for years.
Mm-hmm.
And the membership in this Survival Skills and Ethics program,
Mm-hmm.
It's a very satisfying thing because what they've been doing is they've been teaching students, young researchers, doctoral students, how to become scientists. Basic skills like how to write a paper, how to get an idea, how to apply for funding, how to plan your career, how to do job searches, interviews, presentations, networking, a lot of really very useful skills. I've been so inspired by them because I attended many of those workshops as a doctoral student and young researcher, and that I have proposed teaching skills like that at our school level. And I've been teaching a course titled Introduction to Doctoral Program, which I also taught in Poland during my Fulbright Fellowship in Poland. I gave it the title Fundamental Tools of a Scientist Benchmark. Essentially the things that you really have to know when you become a scientist. And it's been very satisfying because you are dealing with usually highly motivated people, young researchers, doctoral students, young faculty, and you are giving them the best of yourself, things that you have learned yourself from your advisors, from people that you have observed as a young researcher, and you just pass on those skills. It's very satisfying. So that's what this survival skills and ethics workshops were about.
I do really think that it's very important because I think that when I'm actually a student in a Master of Science, and I think everything is not only about topics or certain topics. You know, I think also these other topics are very important, and usually they are not a part of the curriculum of some universities.
So you asked me about my teaching. So this is really one of the things I really love teaching, and it's a relaxing type of teaching because you are teaching things that are, sometimes they're in books, but very often they are just passed from generation to generation, things that I learned from my advisors and then I pass them on. And there's another course that is a service type course that's what we call it in academia. This is a course that is outside of my area of research, but it has to be taught. And I'm teaching research design, which is also a very satisfactory course. You teach people how to set up experiments, how to do empirical studies. It's a very important type of skill for every scientist that does empirical work, experimental empirical work. And it's important because you are learning the nature, the world around you. I'm also teaching two courses that are closer to my area of research, and I'm teaching them on a permanent basis every year. One of them is decision analysis and decision support systems. Mm-hmm. I'm teaching our master students mainly, although there are doctoral students who take that class also. I'm teaching them about foundations of decision theory and decision analysis, which is applied decision theory, the art of and craft of applying decision theory in practice. And also methodologies to use these ideas in building computer-based decision support systems that are based on sound foundations of decision theory and decision analysis. And I'm also teaching, I just started teaching it last year, a course on data analytics, which is related to the recent fashion of big data. Essentially, everybody is collecting data these days in the 21st century. Mm-hmm. And the whole course is about collecting, storing, and processing large amounts of data. So that's the second course that is fairly close to my research area that I've been teaching.
What are the major challenges about managing this big data nowadays? I mean, about the collection and about the processing of this big data.
The term big data is, in my opinion, it's a fad, a term that will probably go away in a few years. It's just fashionable. Because people have been dealing with big data for the last 50 years. When the computers first originated, we had computer storage, internal memory and external space, that was always too small for the data. So in a way, people have been always dealing with big data. Mm-hmm. But what happened recently is the quantities of data have indeed become very, very large, and the gap between what we can store and what we are collecting is becoming bigger and bigger. So I think from the technical point of view, the biggest challenge is to store the data and to process it physically. Let me give you an example. If you have a hard drive that is the size of 3 terabytes,
okay,
and this is not unusual in small computers these days. In order to read the entire drive, it will take you probably a few hours, 2-3 hours, to read all the data into memory.
mm-hmm.
Of course, the memory is not large enough, so you have to process the data when reading. But reading that data will take you 3 hours, say. So the idea, the main idea that is underlying this concept of big data is to make it distributed. Instead of having one computer with a 3 terabyte disk drive, you have 1,000 computers with much smaller disk drives. If you have 1,000 computers, then you can divide that big data file of 3 terabyte into 1,000 disks that have 3 gigabytes.
Mm-hmm.
And reading 3 gigabytes will take you just a few minutes. So, and you have 1,000 computers to process that 3 gigabyte data, which is much, much smaller. You reduce that processing time from 3 hours to a few minutes, and that's the big idea of the big data, I think.
Okay.
It's just a good, sound engineering idea that is used to close the gap between the amount of data collected and the amount of data processed.
Mm-hmm.
I think a good sound engineering idea, but as I said, big data is not a problem that started a few years ago. It started 50 years ago, probably. There was always too much data.
Okay. So, Marek, in your teaching experience, I think that part of this teaching is made on the distance?
Yes, that's right. I have been working at the University of Pittsburg, but I also work part-time as a faculty in Department of Computer Science in Białystok University of Technology in Poland. Because of that, I spent a large part of the year in Poland, and then I'm leaving my lab for almost 4 months. At the same time, when I'm in Pittsburgh, I'm leaving my students in Poland for 8 months. So very often I have to meet with them virtually through through computer usually. Most of the time we use Skype and talk, have our weekly meetings through Skype. We share our screens. It's really, of course, it's harder than meeting face to face, but meeting through Skype has also great advantages. And the same happens with collaborations. You usually these days meet virtually. I have many collaborations with people outside of University of Pittsburgh. Among others, I have collaborated for a number of years with a faculty at UNED, Professor Javier Diaz, and most of the time we've been working through internet, even though we meet occasionally. So kind of from that perspective, I think that UNED has a great advantage over other universities in terms of the experience that you have in teaching at a distance. I realize that teaching at a distance is a difficult thing, and but it's happening more and more. People are learning at a distance, and the difficulties that you have somehow gained experience with is probably your cutting edge, your advantage these days.
Yeah, I think so also. As you talked about topics that were close to your research interest, your research group is the Decision System Laboratory. What can you tell us about your work in this Decision Systems Laboratory?
When I started working as a professor at the University of Pittsburgh, that was 1993, I was first a young faculty still trying to make his name and to publish and gain students. When I got my first students, I realized that it's very important for people to have to be in a physical proximity from one another, to have one space where you can meet and interact with one another. And so physical workspace and physical closeness, in addition to just having a feeling of a team and working on similar projects together. So that was the time when I created the Decision Systems Lab. I gave it a name. I managed to find physical space in the building. In academia, in universities, it's always difficult to find space. There's always too little space. It's almost like we are dealing with a big student body. So I was very lucky to find some space, and then we got bigger space and bigger space. I had anywhere between 2 and 12 students. At some point, the laboratory was 12 students big, 12 doctoral students big. At this point, I think it's around 5 or 6. So it varies. It really depends on the projects we have and the people I have. So I gave this. I tried to create this feeling of physical proximity and also mental proximity in the sense of dealing with the same type of problems. So that's how the idea of Decision Systems Laboratory originated.
Okay.
And then we, of course, the direction that we went into with the laboratory, I wanted it to go in the direction of systems based on sound foundations of probability theory and decision theory. So one of the directions was, of course, theoretical contributions, because the methods are well rooted in econometrics, in statistics, in artificial intelligence, mathematics. So we started working on theoretical ideas, on algorithms. Very quickly we made contributions to inference, to learning algorithms. Our lab is quite well known for contributions to stochastic sampling algorithms. We probably are. There are several labs, of course, in the world that have been working on this, but I suspect that our algorithms belong still to the top in terms of speed and accuracy that they get.
Okay, but you are also known. Well, I think that these algorithms you are talking about are part of 2 pieces of software that are called Jenny and Smile.
That's right. So we have, as one of the things that was uniting us in the Decision Systems Laboratory, we very quickly decided to create a piece of software. You know, it started around 1995, which is almost 18 years ago.
Uh-huh.
And it was a decision. I would say it was a management decision on my part. Why did I decide to do it? It has benefits and also bad things about this. So the bad things about it for the students is that at some point we decided to release the software to the public, to make it available to everybody in the world.
Mm-hmm.
That means that whenever a student that does a piece of programming, it has to be high quality, because we don't want to become known for poor quality software. So that's the bad thing. Additional work that they have to do to make it industrial quality that we are not ashamed of. On the other hand, the good things are that students, when they start, they already have a working, reliable system. It's enough for them just to learn how to use it rather than to program it from scratch. So that usually cuts the time that they need to become productive by a year, I think. So every new student saves a lot of time. Every old student, of course, once you are making contributions, you have to do extra work to make it reliable.
Mm-hmm.
And then building a piece of software also, of course, requires implementing some things that were not research. We just there were public domain ideas published by other people, so we had to implement this. But luckily, I've been very lucky with funding, so I always had a full-time programmer who was able to do the programming. So we created this piece of software. We made it available to people worldwide on our website in 1998,
Mm-hmm.
and since then it's gotten better and better as many users. I think we have over 30,000 downloads. Many of them are just one semester downloads by students for courses, but I know of a good number of industrial applications, some heavy industrial users belonging to large corporations, many researchers using the software. It's very fast, it's reliable, and it has a great user interface. that have been, one of our research directions was user interfaces, so we've really paid attention to it.
Is there anything that you could emphasize about how the projects have evolved since the mid-90s, when they started?
It's actually a very good question, because I wasn't trained as a project manager. I was as a professor, so I had to learn a lot of things. One of the discoveries that I made is that as the software becomes larger, unfortunately the maintenance becomes exponentially difficult. So the movement from 10,000 lines of code to 20,000 requires you probably 5 times as much in terms of maintenance. If you change a piece of software somewhere, you need to retest it again, because unconsciously you may have made a change that impacted other modules. Mm-hmm. So management of a project like this is a difficult thing, and that is probably one of the reasons that it's very hard to create and maintain successfully for a long time a software project in academia. But we have been very lucky, and I have had really excellent people working on it, especially my 2 programmers. The first one was a Spanish programmer, Dani Garcia. Mm-hmm. He really came from Spain to work with us. He left us to pursue other interests, but he was really great. And since the year 2000, I've had an excellent programmer from Poland, Tomek Sowiński, who has done a lot of excellent contributions to the software. And of course, my doctoral students were also very good. I've been very privileged with working with them.
Okay, so I have asked you about how these projects have evolved in the mid-90s, but what can you tell us about the projects these days? What kinds of research are you doing in them?
We've done a lot of work on inference algorithms in the past. Currently, I would say our exact inference algorithms belong to the fastest in the world. I don't know whether they are the fastest, but they belong to the fastest, and the same with stochastic sampling. Currently, a lot of our work is focusing on learning, on data analysis and learning, because this is the important thing. It relies on inference, but it's an important thing, and we want to also get a really leading role in that. We are also working in strategic planning, business intelligence. That is also resting on data analysis. Mm-hmm. One of the most recent projects is writing a cloud library for Bayesian networks. A cloud library means that we can process data in a distributed way, in parallel fashion. I mentioned to you this big data idea, working instead of on one computer on a network of thousands of computers. We would like to be able to do the data processing on thousands of computers, doing it correctly, but in parallel. And that's our most recent project that we have been focusing on. The result of this project is going to be an open source library for clusters, which we plan to release to the world, again, as a service to the community.
Which is the most difficult part in this project, in this cloud library?
I guess the hardest part is developing parallel algorithms for inference and for learning. And some algorithms are suitable for parallelizing them, but others are not. And the difficult theoretical part will be noticing parallelism in those algorithms, developing new algorithms that are parallel. And
talking about contributions, is there anything that you think that both Jenny and Smile have contributed to the artificial intelligence community?
I think definitely. Of course, everything that we have developed in terms of ideas in the lab, we have published. There is nothing that we kept secret here. So everything is published, and anybody can pick up these ideas and implement them. But implementing them ourselves and making them available to the community gave people a tool that is reliable, that is very fast, that they can trust, it's fairly well documented, and that people can use in their projects. That also cuts their time that they need to spend starting their projects. So I believe this is the main contribution that we've made, making the tool available. People can start using them. So not only in artificial intelligence, but in many other disciplines, we have people using the software in industry, in disciplines like geographic information systems, biology, business schools, really very widely. So perhaps another contributions that we've made was making these methods popular in the world. Not only us, of course, there are many research groups and many companies promoting these ideas, but we have definitely made our share in terms of contributions.
Part of your research has been focused on applying Bayesian networks to medicine. How do you think that medicine can be benefit from this kind of probabilistic graphical model?
I think medicine is a wonderful area for these methodologies. It's amazingly good because there's so much noise in medicine. Any type of data is essentially noisy. You cannot say that somebody who smokes will develop lung cancer. You just say that smoking increases the probability of lung cancer. And so is with every disease, every symptom. It just gives you an indication, but very rarely with absolute certainty. So this is exactly where you want to apply probabilistic methods. Unfortunately, in my experience, medicine is a very conservative area. So there have been many brilliant, many smart people building wonderful systems for medicine, but regretfully, very few of them were really applied and put into practice. This, I believe, has to change over time because of this strive for efficiency, for avoiding physician errors. So there are many ideas that are actually making it into medicine. Reminder systems, for example, computer systems that are monitoring patient data, electronic data in hospitals that automatically discover problems, reminding physicians to come to the patient, to re-examine the patient, to pay attention because some medical test came out abnormal, or medicine that are in conflict. All of this is uncertain knowledge that can be monitored and processed automatically, and physicians can be made alert of that. So medicine is a difficult area, even though it's a great area for these methods. But we shouldn't forget that there are other great applications of these methodologies that are in industrial use. We are aware of quite a number of users of our software, and of course there are many other pieces of software in this area. We have several users that are applying this successfully in for example, diagnosis of machines. Engineers are not conservative at all. They are taking whatever works.
Well, it's not the same, the human body as a machine. Yes, well, it can be.
Yes, of course, the consequence of errors is also smaller.
Yes.
So people think that they can trust machines better. They can trust algorithms better. In medicine, people believe that a human being can make a better decision. Of course, there is a lot of evidence that it's a wrong statement. Algorithms are probably better than humans, including medicine.
Do you think that someday we will rely on the decisions of machines?
I think so. We are already relying on decisions of machines. Look at all the difficult places like flying airplanes. Most of the time, airplanes are flown by machines.
Well, I tend to think that someone is driving the plane, but maybe I'm wrong.
I think, I've never been a pilot. I'm not a pilot. I think that most of the time it's the machines that are flying the airplanes, and the pilots are there to just make sure that there is no really clear error on the part of a machine. I think a modern cockpit is one where there is a machine and a dog and a pilot. The machine flies the airplane, and the dog makes sure that the humans don't touch anything. I'm joking, of course, but that is, I think, the future. And also, we are driving cars. Increasingly, there is more and more automation in cars. There are warning systems. There are cameras. There are sounds being made that are warning a driver. There are definitely experimental machines, cars, even cars that are, I think, in production, that are able to engage brakes when they see that the speed is too high and there is something in front of the car. They actually engage brakes without the driver.
Well, nowadays we have some cars that are able to park themselves, no? They have a kind of parking system.
I think that this is inevitable. Medicine, unfortunately, is very resistant to that.
Yes.
But other applications are definitely, there is machines controlling the production processes, looking at the data. One of the big applications of this methodology is in data analysis. Mm-hmm. Things that are, of course, autonomous, like this algorithms monitoring what is happening in the system, but also algorithms that are used by people, like in strategic planning, monitoring an organization, a business, and looking for opportunities. You can do that automatically also. And there is evidence from psychology that machines, algorithms doing this are probably better than humans. Humans are better in some things. Machines are better in other things.
Well, maybe because, I don't know, but maybe it's because it's difficult to kind of emulate the human brain. I mean, how we make decisions.
That's true. These methodologies are often not emulating the brain, but they are based on other approaches. So, for example, take a task like multiplying two 15-digit numbers. Mm-hmm. The human brain is very powerful, but we are not very well suited for this task. If you ask to multiply 15-digit numbers, it's going to take you a little bit of time.
Yes.
The computers are very good at it. So it's just, the type of tasks. And computers are not emulating a human brain when multiplying those numbers. They are using different methodology. They are using a simple algorithm from algebra. So I guess it's the same with applications. Depending on the task, certain algorithms, certain machines will be stronger than human brain. And of course, human brain has incredible strengths in some areas, some applications.
Well, I think that there are a lot of pretty interesting things that have arisen in this interview, and I would like to thank you for your time.
Thank you very much. Thank you.
Sistemas Inteligentes.